Hi. In the last video, I started expanding this control logic circuit and realized that I had kind of painted myself into a corner with this. And so I started taking this apart so that I could replace it with this circuit, which now has 24 control signals that can be used to control the build and has room to expand that up above to additional boards if I am so inclined to do so, and I will be in the future. So what's left to do here is I want to build a strip board for connecting up all of the different address lines here. I want to be able to extend them out to the strip board and then bring them back, make it a little bit easier for taking these EEPROMs out of the circuit. I've got some control logic program changes to make so that I can identify and clarify exactly which of these bits are actually going to control which piece of the circuitry. Once I identify all of that and get that set in the code, then I can turn around and complete the build out, taking out some of the things like the AND gates and the demultiplexers and dropping them in here where they're appropriate to do so. Got to complete that build, and then I can reintroduce this new control circuit back into the overall circuit build and start testing again. And ultimately, the test that I need to complete is make sure that the no-op instruction still works. There's still a lot to do. I'm hoping to wrap this up in one video. Let's get right into it.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Okay, so my goal is to take these 8 jumpers here, these headers, and drop them into this strip board here, such that I can take up to 4 different EEPROM and drop their addresses into here and have it turn around and drive the address locations of the EEPROM. And so I want to solder this up. These get a little wobbly, so I want to make sure that I get them soldered properly. Additionally, it's a little tough to actually solder on this strip board, simply because it doesn't have any solder mask or anything on it. I've got some captain's tape to help me and a little bit thicker solder because they tend to take quite a bit of solder to fill these holes and what have you. That's my goal today. Let's see how far I can get with that. Yeah, I'm going to check this just to make sure that I didn't bridge anything. That's good. Now the next step here is to, and I managed to bend that over a little bit. The next step here is to drop in these additional headers and get them taped up and solder them all in. Now it's interesting to note that I'm doing this at a much higher angle because I've got all of the pin headers in, or sockets in, I should say. And the reason I can do that is because there's already some solder that's in there that the tip makes contact with. And when the tip makes contact with it, it actually melts that existing solder, providing heat transfer to the copper, more so than just the tip itself would do. So with actually, once you get the first connection done, the rest of them take actually pretty darn good. Let's bring out continuity tester again, and we'll test to make sure I didn't bridge anything. That works. So here are the changes I made to the control logic. Obviously, I've got a new comment up here. But the big change is really this enum of constants. I was able to reduce the number of bits that we use to assert to address bus 1. Now, address bus 1 is the address bus which handles the fetch logic for an instruction. So it's the one that's reading the next instruction that's to be executed. Something is always going to be asserting onto that bus. Something is always going to be asserting onto that bus. So it's going to be either the program counter, the return address register, and those are going to be swappable, turning the program counter into the return address and the return address into the program counter as you call functions. And then I'm planning on an interrupt program counter and an interrupt return address. So there's going to be some context there that allows us to handle the interrupt versus user related code. I've got a new bit here, control bit here, which is going to be for main bus group 0 or main bus group 1. And those are the two groups on the bottom of the breadboard, which are going to control what is actually asserting onto the main bus and where that actually comes from. And so this now all becomes the control 1 logic. There are 5 bits that are unused so far, so I've got some room to grow there for control EEPROM 1. Control EEPROM 2, I moved the program counter increment decrement load logic in there, and I've added in the R1 increment decrement load logic in there. I see a typo in my comment here. May as well go ahead and correct that now. And then for control 3, what I've got is I've got my AND latches. So R1 AND latch, program counter AND latch. And those are the two registers I'll be playing with so far. I do expect that the program counter and latch signal is going to be pushed out a little bit, so I'm not going to make that a permanent wiring job yet. It will eventually fall into one of the higher numbers or farther out. Another change I made here is I did have the PROM buffer size to be 8 bits, and now I've changed those to be 64 bits to hold the the 3 EEPROM bytes. I did change the name of the program counter and latch signal, so that's been picked up as well. And then the other major change is simply in how I'm processing the data. So the buffer still is now 8 bytes long. I am splitting that up and writing it out to 3 different files all at once. So I go and loop through each of the bytes and output it directly. So those are the changes I've made to the control prom build. And again, if I come down here and I type make, it does a couple of things. It actually builds this EEPROM executable, and then it will output at the same time the 3 control EEPROMs. Those are the binaries for those. So that now tells me, closing diff here, that will tell me where I intend to put each of those signals and how to wire them up. So now I can break out the breadboards and start getting those all wired up. Okay, the first thing I want to do is I want to work on the address bus 1 assert. I'm going to use this demultiplexer in order to do that, not place there. But I also need to add in a delay for those signals. So I'm going to start with the delay. And I'll drop the XOR in here and wire up power and ground. And I'll go ahead and drop in a decoupling cap for that. And then I'll use the top 2 gates up here, and I'll just drop in some 0 bits. So my second input into here are going to be the two most significant bits off this latch. And just wiggle these wires in between what I've already done for now. I will come back and clean this up. Now the output of those are going to go into the demultiplexer. So once again, I will do power and ground. Now, pin 7 here is an output. Pin 6 is a active high enable. Next one down, pin 5, is an active low enable. Next one down from that is another active low enable. The next one down from that, I'm putting this in the wrong spot. Next one down from that, this is pin 3 now. This is C. And since I want to use only 2 input bits, I need to tie the 3rd bit high. So this is the most significant bit, which is always going to be 0. That's going to force my outputs to be up here. And then I can now take the outputs of these least significant bits here, or most significant bits, that have been buffered now. So that gives me the delay that I need, and drop them in here. Now, the challenge is that these have to cross. So my least significant bit of the 2 comes over here, and then its output has to go to A, which is the least significant bit in this demultiplexer. And so that's going to give me the 4 signals I need up here on the top up here. Let me get another decoupling cap on here. Let me get that cleaned up a little bit. That now gives me the outputs I need here for the the address bus 1 assert. The next bit along is going to be the main bus assert group selection. So that is going to be bit 5. Let's see, I believe it's that one, which I'm going to tie to one of the inputs of this exclusive OR, and then I'm going to actually carry it over to the other input of the exclusive OR. And the reason I'm going to do that is because I'm going to have one that is inverted and one that is not inverted. That's the not inverted, and this will be the inverted. And so now why do I want to do that? I want to do that because what I want to do is I want to drive the selection of either of these 2 groups based on whether or not this is a 1 or a 0. And so if it is a 0, the output is here. That will come down here to, this point right here, which then activates that small group. And then the inverted, so if it's a 1, it's going to get inverted to a 0, and then that'll come and drive that group there. Now, as for timing here for the main bus group select, I don't believe I'm going to have a timing problem here because my hope is to have data asserted to the main bus as early as possible so that it can be latched relatively easily. I may have to put another delay in, but I'll have to measure that to make that determination. I'm not going to be able to make that determination here because I really actually need to see this happen in real life. So let me get this now wired up and we'll see how that goes. You know, that's quite fun, the three-dimensional nature of wiring these things up. We'll call it art just so I don't get criticized too harshly for it. Okay, that takes care of then the 2 signals coming out of this control ROM 1 off of this latch. The next set of signals are related to load, increment, and decrement, and these need to be ANDed with the inverted clock. And so to do that, I'm going to add this AND in there, and then add power and ground, and try to do that without folding the wire in half, Adam. All right, let's try power again. See if I can get it to go in straight this time. Okay, so the next thing I need to do is extend out the inverted clock, which, if you recall, I designated the orange as the inverted clock, so I need to extend that out to each one of these AND gates. Okay, that then gives me my inverted clock to each of those AND gates. And then it's just a matter of extending 1 and 2 3 and 4. So extending those 4 signals in, and then the top 2 become R1, the bottom 2 become PC, program counter. And I'm debating whether or not I want to leave these as temporaries. I may leave them as something that I can easily relocate and tie in later. Okay, let me get these wired up. That then wraps up the 2 sets of load increment and decrement signals. And so these 2 outputs up here, where I've got the wires, will be for the R1 register. And then these 2 outputs down here now will be for the program counter, at least temporarily, until I decide I need to move those. Reality is I don't have to rewire it when I move it. I'll just change where the signals are here and then change the connection points there. The last set of control signals to look at today is going to be related to the AND latch, and that's going to be controlled by the control circuit 3. The challenge here is that we have redefined what that signal looks like ultimately. While the actual logic of generating it doesn't change, the number of signals we can generate and the ICs that we can use, therefore, to generate that signal do change. And for that, we need to take a look at the timing gaps again to make sure that we're as close as possible. Well, I should say as close as possible to the other signals. So what we're talking about here is the AND latch. And again, the signal itself is the signal NANDed with the inverse clock. Of course, we need to use a NAND gate in order to do that. But because I'm no longer using the 74LS138 demultiplexer, I have to come up with some way of handling or finding that extra 39 nanoseconds or so. Put that back into the timing delay. And if anything, I really actually want that timing to be slightly after this, slightly later than this load increment and decrement. So what I've added here is this double inversion, which turns out to be 48 nanoseconds. And if I select that, I actually come in with LS logic at 45 nanoseconds. Not quite the 66, but when I get into the typical for the HC, which is ultimately where I'm going to be landing, it looks like 27 versus 28 is very reasonable. That's pretty much in the ballpark there. Now, I said slightly after. We'll have to take a look at it and see how that all pans out. It may end up being that I have to do something different than a double inversion in order to get that delay. But there's, with just the NAND gate, the typical is 9 to 10 nanoseconds, and that's nowhere near the 27, 20, 30, 39 nanoseconds that I'm dealing with some of these other typical signals. So I'm going to start with a double inversion of those signals to help get the timing right, and that's going to be the 74LS04 IC. And then I'm going to run that through the NAND gate with the inverted clock, and that should then give me the right delay that I need on this signal. So once again, we'll start with power and ground. And then for the two signals that I'm going to start with up here on the top, I'll bring those out, double invert them, and then extend those then over to the NAND gates. And I have to extend the inverted clock signal over to the NAND gate as well. So let me get those wired up, very similar to what we've done down here. So I'll go straight to the final wiring here and get this all finalized here. So that then gives me the two most significant bits coming out here to an inverter each on top. The output of that inverter is then taken over to the first inverter and the second inverter on the bottom. The output of that is NANDed with the inverted clock coming over here in the orange and then continuing on here. So the outputs here and here become my register 1 and latch and my program counter and latch. Okay, with that, it's time to get the build back out and get it reintegrated back in. Okay, I spent a good couple of days thinking about what was left and debating whether or not to end this video here or press on and make a slightly longer video. I've chosen to end the video here, and the reason I did is because I've got so much that I actually need to dress up and reattach in order to get this working. Plus, I've got some rework to do because I realized that these connections here, along with this one in particular, unfortunately were not set properly for my second free running test. So I need to fix this and address those and make sure that I get everything hooked back up properly. I've got this board here that's going to be a landing zone for all the different controls that can be asserted onto all the different modules, and so I need to get all this wired back up properly as well. I just feel like it's going to take too long and I'm going to end up with another 45-minute video. I'd rather split that into two 25-minute videos. So I'll end that here. Again, I'm going to continue to press on here, and so I will continue to do work. I do have a new laptop that I'm going to swap in for my old one. Hopefully I'll get a little bit better video quality out of that. So I'm going to spend a little bit of time on that, but I've got it mostly prepared. I just need to move my stuff over to this new laptop. So that'll take me a little bit of time to do, but that's one of those things that can happen overnight. So thank you for your time. I appreciate it. And look for number 3, where I actually hook this back up, do some testing. I've got some code to write again, I think. So I'll have to see how that goes as I get into it and start doing a little bit more work on this. Thank you. We'll see you soon.